So now we're going to look more in depth at both temperature and catalysts. So let's start out by thinking about what we really mean when we say temperature. So if you think about the temperature of any sample, you can plot it as the energy of the particles versus the percentage of particles with that energy. And there's always going to be some sort of median energy that represents your temperature where you're going to have the most particles. But you're always going to have some particles that have lower energy and some particles that have higher energy. And one of the things that this helps to explain is, for example, when you sweat, as water evaporates off your skin, why does that produce a cooling feeling? Well, here's our graph again. And let's say that above this point right here, that these molecules have enough energy to evaporate. And so everything over here goes into the gas phase. Well, what's left behind? What's left behind is all of this. But because we've removed the highest energy particles from the sample, overall the temperature goes down. And so this is why over time, it takes a long time, but slowly, a glass of water will eventually all evaporate. Or what happens, for example, if you leave, a tray of ice cubes in the freezer for too long of a period? This is also why other liquids produce that cooling sensation in even stronger amounts. So who has ever used acetone? Acetone is the following organic molecule. With this chemical form, with this structure. So acetone is something that as an organic chemist, I go through a ton of. We actually use it to wash all of our glassware. You may more commonly know it as nail polish remover. But if you've ever gotten any acetone on your skin feels cold very quickly. And that's because acetone has a much lower boiling point than water. And so whereas if this was water on this graph, maybe this percentage of the molecules will evaporate. But acetone, with its lower boiling point, has a lot more that will evaporate. And so that cooling feeling ends up becoming a lot stronger, a lot more quickly. All right, well, what does that have to do with the rates of reaction? So here's our graph again. And let's say this energy right here is our activation energy. Well, if we raise the temperature, now maybe our graph looks like this. And so as a result, instead of just a few molecules having enough energy to reach the activation energy, at this higher temperature, a lot more of them do. And so at higher temperature, we have more energy, and the reaction can take place more quickly. All right, let's go back to catalysts now. So we said that a catalyst is a substance that increases the rate of the reaction, but is not consumed by the reaction. So how do catalysts work? And what are the most important catalysts we know of? Well, those would be what we think of as biological catalysts, or enzymes. So they work in one of two ways. They work by reducing the activation energy, and they also work by increasing what we call the frequency factor. And the frequency factor is just known as the number of collisions. So let's see how this works. So here's the reaction of hydrogen peroxide decomposing to form water and oxygen. The activation energy of this reaction is 76 kilojoules per mole. But what happens if we add an iodide ion to this reaction? What happens? Well, the first thing is that it changes what is called the reaction mechanism. The reaction mechanism is a situation where we might draw a reaction out as A reacts to form B. But it doesn't necessarily happen in just a single step. We might find that A reacts to form C, and then C reacts to form D, and then D reacts to form B. And so ultimately the overall reaction, the net result, is that A reacts to form B. And when we add iodide to this decomposition of hydrogen peroxide, the mechanism now takes two steps. So hydrogen peroxide reacts with I- to form water plus IO-. Another molecule of peroxide then reacts with IO- to form water, oxygen, and I-. So notice that net we get the same reaction. Two molecules of hydrogen peroxide, one here and one here, react. They form two molecules of water and one molecule of oxygen. Now the activation energy for this process is only 56 kilojoules per mole. So you can see we've decreased the activation energy by 20 kilojoules here. But what about these other two species? I- and IO-. What are they? Well, that's not what we wanted. It brought over the highlighting, but not any of the text, so we'll just rewrite it. So again, we know what the peroxide is. That's our starting material. We know what the water and the oxygen are. Those are our products. But the I-, that's our catalyst. It's something extra that we added, and it got used, but at the end it got regenerated. So during this reaction, the I minus got used and it got reformed. Therefore, the net is that the amount of iodide didn't change. What is the IO minus? So the IO minus, you can see, is formed in the first step and reacts in the second step. So this is known as an intermediate. Intermediates are very, very short-lived species. You can't isolate them during a reaction, but they're made and then they're immediately used up. Now, as we continue to talk about reaction rates, and we're going to go back to our simple reaction, A going to B, if we plot concentration versus time, we find something that happens like this. So our starting material, we start out with a lot of it, and it slowly decreases over time, eventually leveling out. With our product B, it probably starts at 0 concentration, goes up, and it levels out also. So at some point, we reach a point where the speed of the reaction A going to B is equal to the rate of the reaction B going back to A. And this point is what we call chemical equilibrium. And that's where we'll pick up in our next video.